So today I'm going to be talking about update strategies for edge devices. This can be a deceptively difficult problem to solve for, especially if you're dealing with a fleet of devices with different capabilities. But there are some tools and design strategies we can put in place that resolve some of the issues we'll run into. So a little bit about me first. My name is Cosgrove. And for the last year, I was an engineer at JFrog on the IoT team, and I recently moved into developer advocacy, which is why I'm here talking to you guys. So what we're trying to do here is bring DevOps to the edge. There's no reason for it to be this difficult to update edge devices still. It's ridiculous. So in pursuit of this goal, we found some interesting solutions and tools that we could use to bring into a CI/CD pipeline for embedded Linux edge devices. To do that, we built a rather flashy demo that put several of those solutions on display. If any of you use JFrog products already, you might have heard about it at our user conference last summer. So we need a little bit of context here. How big is the edge? It's pretty big. Counting both dumb sensor edge devices and smarter devices like gateways or what you would hear in like consumer media referred to as IoT devices, it's about 20.4 billion devices. That's nuts. That's a lot of devices. Think about how many people are on the planet. We're at like, what, 8 billion now? So we're radically outnumbered by these devices. And how are we updating them right now? We're kind of not for some of them. They're throwaway devices considered effectively single use. When they break, you have to just replace it. A lot of those that are being updated are doing it in a way that's a little bit unwieldy. It's time consuming, or the infrastructure to support it is complicated, or it can't happen wirelessly and requires physical access, which is irritating for users, and for the manufacturer can cost money in time spent having an engineer go on site to reflash the devices. But the edge industry is booming. It's massive. We're making a lot of money on this in spite of the fact that it's currently kind of inconvenient. So why should we bother putting forth the effort to fix this? It's really, really inconvenient. And it's just going to get more inconvenient the bigger this gets. It's taking over a huge amount of work in multiple industries: consumer, industrial, medical. Building automation is frequently just a collection of edge devices now. And those slow over-the-air updates are also kind of annoying. So it's also really dangerous. Infrequent or non-existent software updates, regardless of the reason for it, present a pretty massive security vulnerability in anybody's network. We're all very aware that unpatched software is a problem. We know that. It could mean allowing anything from the exposure of user data to a malicious third party to your devices being harnessed for botnets or cryptocurrency mining. Both of those things have happened on a really wide scale recently. That's a fairly common occurrence, unfortunately. And the safety implications for medical devices are also pretty extreme. Medical devices are generally intended to stay in place for several years. So that's several years without any kind of hardware or infrastructure updates. So what is slowing us down? Why is this problem not getting solved? We aren't building for it. Many devices are just not made to be updated, like I said earlier. They expect to run the software version that they ship with until they break. The update strategy for those devices is usually just flashing them. This is dangerous because how often have you shipped a piece of software that has 0 bugs in it? Anybody ever done that before? No. Yeah, you shouldn't be that confident in your QA team, because there are between 1 and 25 bugs per 1,000 lines of code. So no matter how confident you are in your abilities and your QA team, there are bugs making it into production. It's just something we've got to accept and plan a way to deal with it. So we're also dealing with a lot of connectivity concerns usually with edge devices. We can't rely on its network. The network's probably unstable. the bandwidth might be low, and the network also probably isn't secure. So we need the updates to be signed in some way so that they're trustworthy. We're also dealing with a lot of hardware variations. It's 20.4 billion devices, so that means a lot of specialized hardware. None of these things are running on any kind of recognizable standard that we can rely on at all. Each class is running on something specialized with differences in communication protocols, amount of memory available, storage space, architecture, even operating system sophistication. They're just not that easy to solve for. So how do we design something that takes into account all of these differences and all of these problems and handles them and makes it easier to deploy to a wider range of devices instead of just a single board or a single device type? I don't think that we're at a point yet where we can design a one-size-fits-all solution. There are just too many small bespoke boards out there. But we can get pretty close. We can get you a one-size-fits-most. So first of all, we've got to stop building devices that can't be updated. It's not acceptable anymore. Besides the glaring security problem and having a fleet of devices out there in the wild collecting data that can't be patched if there's a software issue, the ecological impact of designing single-use electronics that might need to just be thrown away because of a bug is totally unacceptable. We got to not do that anymore. There are so many of these throwaway devices out there that the medals for the Tokyo 2020 Olympics are entirely made out of metal harvested from thrown away electronics. That's astounding. Think of the number of medals in the Olympics. So we also need to start designing with the philosophy that your product should improve over time, at least over its usable lifespan. This might not apply to dumb edge devices that are just like an array of sensors sending data back somewhere else, but it certainly applies to the smarter ones and gateways and whatnot. The expected lifetime of some of these devices is 5 to 10 years. They should not just be getting worse from the day they ship. We need to be building more robustly. A bad update should not brick the device. There needs to be a way to roll back immediately if something goes wrong. Your updates need to be trustworthy, or your users aren't going to use your products. So on to the proof of concept. To drive this point home, we built a proof of concept using the most tangible example of an edge device we could think of, a car. A lot of people don't like to think of cars as edge devices, but there's at least one computer in that modern car, sometimes 3, collecting a lot of data about what you're doing and doing something with that data on site. It's an edge device. There's computers in there. So what are cars like now? The overwhelming majority of cars can't receive software updates over the air. They need to be brought into a service center to do it, and it takes hours. Cars that can update over the air still take a while to do it. Tesla, I think, an hour or 2, and the car can't be driven while that's going on, which, may be fair. Different cars are using different boards and running on different operating systems. Even within one corner of the market, we still don't have any kind of standardization. And 15% of vehicle recalls are the result of bad software. For example, Jaguar had a mass recall maybe a year and a half ago that was a result of a bad software update that caused a problem with the braking system. So that's pretty serious. It's a cause for concern. There was also a car that could update over the air, but it couldn't roll back in the event of a problem, and it trapped its user in the car on the highway for hours. So cars as edge devices. This is a very real, very painful, very potentially dangerous problem. So there were a lot of things we could solve for here. It made a really good use case for us. It's tangible for both end users and for manufacturers. So it's relevant to the car companies, and it's relevant to me or you, anybody who owns a car, pretty much. So because we were working with a car, we were very motivated to make sure that this happened quickly and that it happened reliably and without the potential for killing the imaginary driver. To simulate the car, we used a Raspberry Pi 3B Plus running automotive-grade Linux strapped to an RC car. You could drive it. It was very fun. So on our workflows and tools, we had two distinct workflows, one for software updates and one for firmware updates. For the software updates, we were updating the apps running on the car without flashing its firmware. It's very quick, it doesn't interrupt the user, and it supports rollbacks. This workflow relied on K3S and Helm. For the firmware updates, it was a little bit more difficult, but it still happens in a few minutes. It still has the ability to automatically roll back if a fault is detected, and it's still relatively low pain for the user. This one relied on Mender and Yocto. So this is what our software workflow looked like. Just a quick overview of the technologies involved here. We used JFrog Artifactory to manage our various build artifacts, as well as handle promoting builds from development to production. X-Ray was used to scan our package dependencies before release, gives us detailed information on vulnerabilities or potential policy violations. K3S and Helm are used to deploy to the car, since it already integrates with JFrog products and a ton of existing CI tools. Pipelines was used to orchestrate it. So the first tool here is K3S. They like to say it's Kubernetes, but 5 less, which I think is very cute. So K3S is just lightweight Kubernetes. It's designed for edge devices. It uses only 512 megabytes of RAM, produces only a 40 megabyte binary, and it has very minimal OS requirements. The packages dependencies are just containerd, flannel, core DNS, CNI, and some utilities like IP tables and SOCAT. We also used Helm, which I assume most of you are already familiar with, so I won't go into like a ton of detail on what Helm is, but its charts can describe some pretty complex applications. It gives you an easily repeatable installation. It's the final authority on your application. The charts are very easy to version, and like we need, it supports quick rollbacks if something goes wrong. So this is just a part of one of the Helm charts from our car demo. It's building a microservice that we were using to allow us to control the miniature car with a racing wheel designed for playing video games. Syntax here is pretty simple. Put some YAML on it. So the result of the software workflow is that application updates were really, really, really fast. About 35 seconds from a developer pushing code to deployment on the car. It doesn't interrupt the user, so this can happen while the device is in use. Not that I think it necessarily should, to be clear. For most updates, I think that there should be consent from the user involved, or we should at least tell them that it's happening. But if you design your edge device with this strategy in mind, it does mean that you can update silently. So if you have an edge device out there that's got no need for user interaction and doesn't need a full firmware update, this is probably a pretty compelling set of tools for you. So our firmware workflow, the overview looks pretty similar. Yocto is used to create our builds. We have pipelines handling all the events again, and X-Ray checking our packages for vulnerabilities and policy violations again. We're also using Artifactory again, but this time for more than just storing binaries. It is handling some of the workload for Yocto by storing its build cache to make things faster later on. And Mender is being used to handle our over-the-air updates portion. So Mender ticks a lot of the boxes we're looking for. Our updates are all signed and verified. It supports automatic rollbacks, again, if something goes wrong. And it provides several distinct installation strategies for us. I'm going to be focusing on the dual A/B strategy. So using this method, we have two partitions on the device, A and B. The bootloader is aware of which one is active and which one is not. Obviously, it's going to boot into the one designated as active. However, during an update, the inactive partition gets updated silently in the background. It's streamed straight to inactive, and then it's designated as active, and on next reboot, it's the one that your device boots into. This is useful for us because it means that if something goes wrong, the inactive partition, it's still there running the old version. And if Mender detects that something is amiss, it won't boot, it barfs too much, it'll just reboot and roll back into the old partition. It's very, very quick. So we still need to deal with the size of our builds, because remember, we've got a probably very slow network here. For that, we use Yocto. It lets you build custom Linux distributions for any hardware architecture. It's pretty neat. It eliminates a lot of your OS bloat, drastically reduces resources used on the board, and minimizes your hardware requirements. Because we're building a distribution without modules that are unnecessary for your hardware. So if you only need to communicate over Wi-Fi, we can build a custom Linux distribution that doesn't include modules for Bluetooth or Ethernet. Bitbake is used to write recipes for the build. It pulls in layers for different hardware configurations and applications. We used a layer for the board itself, a Raspberry Pi 3B+, as well as layers for K3S and Mender. Yocto already provides a ton of hardware layers for common configurations to get you started really quickly, and you can write custom layers to isolate specific applications or behaviors. As an example, this is part of the meta layer that adds K3S to our Yocto build. It's just Bitbake syntax. It's pretty straightforward, and it lets you execute both Python and shell scripts in parallel. Getting Artifactory involved, the first build is going to take a while, and there's just not a lot we can do about that. It's going to be faster than building a whole standard Linux distribution, but it's still building a Linux distribution, so it's going to be a little laggy. But after the first build, we can speed things up a lot. Yocto caches everything it downloads, and we can make it use that cache for future builds. That way, it's only rebuilding what changes. So what we do is we store the build cache in Artifactory every time we build, and we point Yocto at that build cache. That way, we can reduce the time required after the first build by up to 50%. I'm not sure if you could get it faster than that. 50% was the most we could manage, but that's still pretty significant. So the result here is that we cut the total build time after the first build to just 5 to 10 minutes. That's built and deployed to the car. The build is as small as we could get it. The updates are signed and secure, and we have automatic rollbacks in case of failure. It can be used to update a system incrementally, and it supports rollbacks, just like we need. There's also a Yocto meta layer available for OS tree. It uses Actualizer to handle over-the-air updates. It's pretty cool. We almost used that instead of Mender, but it was more fun to package in another thing. OS tree is also used by a few different Linux distributions to manage their own updates. We also have Lava. It's a testing framework for operating systems on embedded devices. It stands for Linaro Automation and Validation Architecture. It's a continuous integration system for deploying systems onto physical and virtual hardware for running tests. It can handle simple boot testing, bootloader testing, or system-level testing. Results are tracked over time, and data can be exported for further analysis. We use this in the lab in Seattle, mostly for device management. So it's designed for validation during development. It's worth noting. This is not something that you would use when deploying to production, because it can be very slow. But it is outstanding when you need to test. Anything from whether changes in the Linux kernel compile or boot, or whether the code produced by GCC is smaller or faster. It can make writing tests for it kind of hard because it can do so much. There's a pretty steep learning curve here, but it's worth messing with. It's also really good at device management. That's not what it was designed to do, but I think that's where it really shines. It has onboard templates for a little bit more than 100 boards built in. If there's something you need it to test that it doesn't natively support, you can write a device profile for it. It's just Jinja 2 templating. It can be hard to integrate it fully. There's a lot of trial and error in doing that, but it's totally possible. This is just an example of what some tests look like in Lava. The first image is 2 devices, a Soka 903 and a High-Key 960. This shows that they've never failed any health checks. They haven't failed any recent manual tests. And these, the second image, are all of the specific tests that are running on the Soka 9. So it's doing a significant amount of work that I don't have to do manually anymore. So let's recap. Edge and IoT updates are kind of broken for a lot of industries right now. The way it's happening is not great, it's inconvenient, it's expensive, and it's dangerous. And we've got to address that. It's a gigantic security flaw. For edge devices running embedded Linux, a modern DevOps pipeline and a handful of open source tools can solve a lot of problems for you that are definitely worth solving. It's fairly low effort to use these tools if you build your product expecting to use these tools. So these are all of the tools we used in one screen. I liked their logos. They were neat. But if you go to jfrog.com/shownotes tomorrow or the next day, I will include links to the documentation for all of these different tools that I mentioned, so you can dig into them a little bit more. Definitely, Lava is very much worth looking into if you need device management. There's just nothing better we've found at scale. Thanks for listening to me. If you have any questions, you can get me on Twitter, or you can email me. And again, everything will be up at jfrog.com/shownotes probably tomorrow. Thanks for listening.